another infinite context transformer has come out, and it is called it's called Infini-attention. Very very strange name. Yeah, this is the paper title. Leave no context behind. Efficient infinite context transformers with Infini-attention. That's definitely a name. So this is a preprint, and it's by Google. And basically, the idea is to take the attention mechanism, adapt it so you can retrain it in a way that allows you to have infinite context, or theoretically infinite context. And the idea they propose is pretty interesting. They have a few things they pull from different sources and kind of combine them together. So Infini-attention. So to start off, I'm going to do attention speedrun. So if you already know attention, skip ahead. If you want a refresher on attention, this may be fine. If you want to learn attention, this is definitely probably not sufficient enough. Anyways, so say I have some matrix S by D, where S is our sequence length, or N, or whatever you want to call it. So maybe this is like 1024 with some number of words in it, and every part of the sequence is a token, so you split this up into a bunch of tokens. So 1024 tokens of size D, and each of these tokens represents usually a word piece. You can think of it as just representing a word. So this will be our matrix X, and what we do with our matrix X is we compute we throw it through three-way matrices. So let me move over here. We throw it through three-way matrices WQ, K, and V, which are all D by D, or I'm just going to simplify it and make it D by D. They actually each have their own dimension, where the K and V dimension have to match and the Q dimension can be different. But I'm just going to simplify it to D by D. And this is our X, and you compute your queries, keys, and values from this. So let me do that. So S by D, these will be our queries. These will be our keys here, S by D. And these will be our values, V, which is also S by D. So query keys and values, I'll actually write it in here, K and V. There we go. And this is just by the three different learnable matrices we have. Now, what you do is you first compute QKT. So, and then you divide by the dimension, or the square root of the dimension, just to keep this is just a normalization factor to keep the values from I think it's just to stabilize the softmax values in the softmax operation. But what this gives you is an S by S matrix, so QKT, where these are your queries, these are your keys, and this will be an S by S matrix, where each of these is a score, which will be used in the output matrix. And usually, and if you want to make this causal, you mask out the upper triangle part of this matrix. So this will become all zeros, or negative infinity before you do the softmax. So then you apply softmax, and this basically gives you a distribution for every row vector. So this will be a distribution over one value, this will be a distribution over two values in the causal case. This will all be in the causal case because the bidirectional case is not used as much and it's more intuitive causally. So then this will have a distribution over three values and so on. So just a bunch of distributions. Now, so Q and K. Now, after you compute this matrix here, you multiply it with your values and you get an output matrix, O, which is S by D. Put it up here. So this first token here will be composed of just this first value here. The second token will be composed of the two values here. So if I had the cat sat on many mats, it's not just a mat this time, then the word the will just be composed of the word the. So this first token here, the word the cat will be composed of some percentage of the and some percentage of cat, and the word sat will be composed of the first three tokens and so on. Like the word many will be composed of some percentage of the, some percentage of cat, some percentage of sat, and some percentage of on, according to the distribution calculated by the query and keys. So this is all that's being done in attention. Now, there's many problems. One problem is before you do this, you have to add positional encodings, and the positional encodings basically force you to have a limited context, because if the model has only learned positional encodings up to, say, a sequence of 512 positions, then once you extrapolate beyond that, it hasn't seen that positional encoding before, so it doesn't know how to deal with it. And in positional encoding, it's just you can think of it as just adding it like some vector to this vector here. So the first token here would get some unique vector representing the first part of the sequence, and the second part will be some unique vector representing the second part of the sequence. You usually do this by sampling sine and cosine waves, or you can do this using relative positional encodings. Anyways, the problem is that it can only learn these it only learns these positional encodings for a fixed window size, and you can't really extrapolate beyond that after it's done training. Another problem is this S-squared matrix, and this here is very computationally heavy. You have to store this whole entire thing in memory, which becomes intractable because it's S-squared. So as you increase sequence length, the memory increases of the order of every other part of the sequence before that. So once I add in a word, it adds memory for every other word in the sequence because of that. So that's another problem. And there's a lot of other problems, but this becomes infeasible whenever you're sampling. So if I'm sampling, say, if I'm sampling like ChatGPT, and I'm just having a chat with it, this matrix is going to become massive. Like S is equal to maybe thousands or tens of thousands. And that means that this matrix here will be the square of whatever that is in memory, which is basically intractable. But it also means another thing is, since you can't extrapolate beyond the positional encodings it was trained on, it makes it hard to sample for a long number of time steps, making it hard to have conversations. So these are the problems which this paper basically attempts to deal with in an interesting way. It basically combines attention with an RNN, like you always do, but there are some interesting formulations that are in here that I want to show. So yeah, so the method here takes from, I think it was two main papers. The first main paper was this paper called Transformer XL, which I think it makes it kind of like an RNN Transformer XL. And another paper is called Transformers are RNNs, which does make it an RNN. So you have these two papers that it kind of bases it off of. Now, the first thing is this. So, well, before that, but basically the idea is we're going to have a RNN compute attention across, where is it? Down here, across segments. So we have our sequence, and we're going to split our sequence into segments. So this will be segment 1, this will be segment 2, this will be segment 3. And the segments are composed of n tokens. So S is our segment number, and n is the number of tokens in each segment. So n can be like 1024, and S is just the index. So this would be index 1, this would be index 2, 3, and so on, and each of these have 1024 tokens in it, or something like that. So some large amount, but not like too large, and you basically just chunk up your sequence into these segments here. Now what we're going to do is we're going to have a hidden state, and the hidden state is going to be passed through one of these segments, and the output of the segment will be a updated hidden state. So this will be H0. It gets passed through this segment, which does some sort of attention on these tokens here. So this segment of tokens, it does a local attention specifically, and it takes in H0 and it basically combines it. So it combines knowledge of all the tokens from the past, as well as all the current tokens, or all the tokens in some fixed window, and then it does the attention output. So this is different from normal attention, where you would have this entire sequence here, and then you would throw it through an attention mechanism, which is, like I said, very intractable because of the S-squared complexity. Now, if you do local attention, this thing doesn't have context of anything in the past, because it's local attention. Attention only has context from the segment it's working on. However, if you have a hidden state that hopefully captures all the information of the past, then you should be able to do a local attention and an update using the hidden state, and hopefully that'll be enough to basically compute this full, or to compute something similar to the full attention, even though you don't have this s squared in terms of memory. It's s squared in terms of, or s squared in terms of the entire sequence length. It's just s squared in terms of the segment, plus this linear part in terms of the RNN hidden state. So that's the idea. Now this part here, this local attention, is just normal attention on the segment. What they add is they add the hidden state. So that's what we'll be going over now. So the hidden state is computed using, I think it was a formula from the RNN paper. And I will show where that comes from right here. So if we have attention, so we have our attention mechanism, and our attention mechanism is just the softmax of QK transpose times the values. Now you can rewrite this because of the softmax formula. You can rewrite this, and I'll subscript this as I. So this would be QI. So I'll subscript this as, just I. And you can rewrite this as basically just the softmax formula. So this will be, and I is just a specific token. So I is just one of the outputs here, just the if output. So let's do this. It'll be the sum from j is equal to 1 to I of the similarity between qi and kj. And I'm actually going to write this in blue, multiplied by vj. And then you divide this by the sum of j is equal to 1 to I. And I write this as I because this is the causal case. If it wasn't causal, this would just be n instead of I. But the causal case is more difficult and it's a lot easier to go from the causal case to the bidirectional case. J, there we go. So this is how you can rewrite it, where the similarity between Q and K, if you want to make this softmax, this will just be X, or I'll make it lowercase, Q and K, is equal to E to the Q transpose K over dk. So this is equivalent to normal attention. Now we can rewrite this again as basically using the kernel trick, where you take the similarity function and you break it up into two. So this is not going to be equivalent, but it's going to be an estimate of softmax, because you can't really break this up. The problem is you can't really break the softmax up. But if we have a different function, a different similarity function, then you can break it up. So j is equal to 1 to I of, we'll call this function phi. So phi qi times phi of kj times vj over the sum of j is equal to 1 of phi of qi times phi of kj. And this is the same thing, just the similarity is broken up into two functions. And this is equivalent, assuming you have a similarity function that can be decomposed like this. Now, for phi, they use elu of x. So phi of x is equal to elu of x plus 1. So just, I think this is it's a ReLU looking function, some function, essentially. Some function that's nice that you can multiply together and have a nice domain. But they use elu plus 1 in this case, and they used elu plus 1 in the paper they pulled this from. I think it was the RNN paper. Now, you may notice that the q's are not indexed by this sum, so you can bring out the q, or you can bring the q outside the sum. This will be j is equal to 1 to I of phi of k, j, vj. I won't write it in blue, or I'll write it in blue once more. J, j, over the sum. This is very sloppy writing, sorry. I guess that's usual. Phi of qi multiplied by phi of kj. There we go. So this is basically the final formulation we have, and what this allows you to do is to independently sum this part here without any influence of q, as well as this part here, which basically gives you an RNN formulation. I forgot the transpose. Transpose, come back. All right, let me bring the transpose back. So transposes go here. Transposes are quite important to have your order of operations right. So this is what we have. And this can be rewritten, which is what they write as a phi of qi times mi. This is actually mi minus 1 over phi of qi times zi minus 1. And this is the exact formula they have here, right here, except they use sigma. And sigma is just elu. They write somewhere. Oh, yeah, elu plus 1 as the activation function. There we go. So this is going to be how we extract information from our RNN. You can think of this part here as our RNN, right here, going over the sequence. So this is the sequence part, the I index, and our queries basically observe this hidden state. So if k and v are of dimension d, which they have more dimensions, it's n by h by d, it would be by 1 by d, well, by s by d, and you're indexing on there. So n by h by s by, or n by h by d. And if you multiply this, you get an outer product. And the outer product creates this matrix, which is going to be a KV matrix. Yes, I think it's KV. Yeah, KV matrix, or rather a phi KV matrix here. And this is essentially your hidden state between every part of the RNN. And you also have this second hidden state here, the normalization factor, which is just going to be a vector storing phi of k. And this will be a kv hidden, so the hidden state at state I is basically the sum. So hidden state at I is equal to the sum, j is equal to 1 to I of ki, ki phi of ki, transpose times phi. And this here is just, so maybe h hat of I is equal to sum, j is equal to 1, I of phi of ki transpose. So basically you have two hidden states in your model. So you can think of this as I have my initial hidden state, and then I send this through a layer, or I send this through the first recursive module, which takes in kv. So this will be k1 v1, and then it's updated, and this will be h1, which is just composed of k1 v1. And then you go through the recurrent module again, which takes in k2 v2, and then it outputs h2, and so on. So this is just our recurrent neural network here, and that's all it's doing. So this formulation here allows you to have a recurrent formulation. That's all. We just took this operation, we changed the similarity scoring, and we turned it into an RNN. Now, what we have over here is the recurrent formulation. Let me do that. So our hidden state, ms, this is going to be our big hidden state. This is our dk by dv hidden state. And this is updated by taking the past hidden state and taking this here. So this is just, oops. This here is just the elu of k multiplied by v, and this is going to be an outer product between the two. So I have it written out up here. And remember, this is going to be our hidden state. This is going to be a hidden state that's computed for this entire segment here. giving us the next hidden state. So this hidden state is going to be updated for all 1024 or segment number of segment or n tokens in this segment at one time. So you take the past hidden state, you update it with all these tokens, and then you get the next hidden state. You're not updating it one token at a time, you're updating it segment at a time. And this is why they formulated like this outer product here. And this outer product is the inner dimension is n, so the number of tokens in your segment, and this gives you a dk by dv, basically giving you this update for the entire segment, and this gives you a dk by dv matrix, removing the head and batch dimension. So this here is going to be a dk by dv matrix, and you just keep updating it with the keys and values of every segment. Yeah, and you can think, yeah, so that's all it's doing. Just every time you reach a segment, update it with all the keys and values in that segment. Now, this is very similar. All you're doing is you're taking the previous norm and you're updating it with this term here. And all this term here is just the denominator. It's the sum. So this is the sum over the segment. So t indexes the segment, is indexing the segment. And you're just summing all the keys sent through the activation function for that segment. And that's all you're doing. You're just taking all the keys in the segment, summing them up, or passing them through the activation function, summing them up, and then using that to update your normalization state. So this is all it's doing. Large hidden state, small hidden state. And then you observe it here using Q. You observe these hidden states using Q. And this gives you your AMEM. That's what they call it. This will be our memory attention, which is how you observe your hidden state attention in quotes mechanism. One thing that they do is they use residuals instead of just V. So it's this formulation here, but they add this term here. And this term is basically saying like how far is the current V from the hidden V. And you can see that they use something similar to AMEM, but they basically they multiply by the activation of K instead. And real quick to show why that makes sense, I can write out over here. So if we have this function here, I'm just going to take exactly what they have over there, which is sigma of k times ms minus 1 over sigma of k zs minus 1. So we're just taking the hidden state and the two hidden states, and this is just the formulation that they're giving over there. And you can just turn this into the sums that they are. So sigma of k multiplied by, so this will be the index over j. J is equal to 1 to I of phi of kj transpose vj over sigma of k times the sum of j is equal to 1 to I phi of kj. And the k's kind of cancel out. You can think of them as canceling out, and this basically gives you the sum of v. So this gives you basically your hidden v, you can think of. And you want to see how your hidden v, this is basically like your hidden v. You want to see how different is your current hidden state of v from the new v that's coming in. And this is just using the delta as opposed to just updating v, or just updating the hidden state with v entirely. Instead, you're doing it by the difference between what your hidden v is and your new v. Now, one thing I've initially thought of is this causal because you're doing this outer product here? And the answer to that is yes, because you update using the previous hidden state. I think that's made evident up here. So this hidden state captures all the keys and values from the segment before. So if we're calculating attention for this segment here, the keys and values come from here, meaning that this attention mechanism here has context from all of these, but it doesn't have context of itself, at least the memory, the RNN attention we're computing, meaning that the multiplication over all M is causal because it only utilizes the memory from the past hidden state. So at the current step, it utilizes the keys and values from the past hidden state, basically observing the hidden state using queries at the current step. So it is causal. And yeah, they also add this, so that's basically the attention mechanism here. They call this a mem. All it's doing is computing this RNN over segments, and you get this a mem value here. Now, how do you combine this with the local attention they have? Because we have this RNN thing that we just created. How do we combine that with normal attention? And all they do is they take the output of this memory attention, which is this here. So observe the hidden state using the queries from the current segment, or using queries from the current token. And you do this full attention, this causal attention over the segments. This is your segment attention, and this is going to be your RNN past attention. I'll put attention in quotes. So this stores your entire context from prior segments, and this computes information from your current segment. And they update it using the sigmoid of some learned scalar beta, allowing it to do some interpolation between either utilizing the past states or the current segment. And then they have the output matrix here, which is normal attention output head mixing. Now, that's basically the entire thing they do. They just add this RNN part to the segments, and it allows them to extrapolate further, because the positional encodings are just on this part here. The positional encodings are not on the entire part. They're just on this local part here. And you have this RNN that hopefully captures all the hidden, or all the information from the past. So this allows you to extrapolate to arbitrary long context, because of this mix of local attention and this global context RNN. And they show pretty good results on the tasks that they have. I think that was, so down here, they show on some long context modeling results compared in terms of average token perplexity. I forget how long they model it. It was either 32,000 length. Yes, so they basically model this on long context up here, on long context language modeling. And you model this in terms of perplexity, and it does quite well compared to the other models here. So this is going to be our causal model, and it's also a lot smaller in terms of memory, because the memory needed is just dk by dv, and h by dk by dv. That's how much memory you need for the hidden state. And this is smaller than other methods such as Transformer XL and memorizing transformers and RMT. And interestingly, the delta doesn't perform that much better than just the normal linear one. And they also note that the segment length is 2048, that's like the segment length. They just pick that segment length arbitrarily, which is basically the context size of a normal transformer. They also do this benchmark here of summarization. So if you have 500,000 words, they want the model to summarize, and it does well on the benchmark as well, showing that it does well on really long contexts. They also have here, I think this benchmark was, you have a bunch of text and you have a password somewhere in the text, and then it has to recall that password, and it does well on that given a large input length. So it does that. It does well on that as well. So the few tasks that they show, it does really well for this infinite context length. And note that this is only with a 2048 segment length. So you have 2048 for the first segment, 2048 for the next segment, and you do that until you reach 500,000. So it can store this information for quite a long time in the hidden state. They also show this cool matrix here, showing that some heads only look at the past, some heads only look at the I think this would be no. So some heads only look at the current segment. Some heads only look at the past, and some heads are a mix, as you would expect. But a lot of them are 0, meaning that they do not utilize this at all. They don't utilize the past at all, and they're only utilizing the current segment memory. So that's quite cool. Yeah, and then sampling. So whenever you're sampling, the reason why it's so effective is because you have your set of tokens here. We'll break this up into segments like this. And you pass this through your transformer after it's trained. So it's passed through the transformer, and this gives you a prediction for the next token for every part of this. So next token predictions like this, and this is going to be your local transformer, your local attention, rather. And you have your hidden state here, which is passed through this local attention, and it gives you the next hidden state. So we'll call this, say, H1, and this represents this entire context here. Now you pass this through your transformer again, so your local attention again, with the new set of tokens. So if you're wanting to predict, say, the next token here, then we need to first give it context of all this. But note that none of this has to be stored in memory at all. This here can just be, this here is all represented by H1, so this can all be thrown out, meaning that we start this with the exact same amount of memory as we had with this. We don't increase the memory at all, so it's constant memory, and this will output a prediction for every token here, as well as another hidden state, so H2. And then we throw this through our attention again, using these tokens, like this. And this will hopefully give us the prediction for the next token here. And note again that we don't need to store any of this. We just need to store our hidden state here and these tokens here to get this next output here. And then if we were to sample another token, so we sample this token, we throw it here. If we were to sample another token, we just throw this sequence back through. We get another token prediction, and yeah, we don't use any more memory than we needed. So this can go on for forever and not increase the amount of memory at all because the hidden state is finite. So yeah, it's quite cool how you can sample with this, but it's cool if it actually works as well as they show here. Yeah, so cool idea nonetheless. This is Infini-attention.